Okay. So good morning. So let's continue lecture 21. We have 26 lectures, so should be able to finish that on time. So last time we introduced this minimum mean square error, MMSE estimation framework. So this framework aims to solve such a minimization problem. We have an underlying random variable x that we want to estimate. But we can only observe another random variable y. This is our observation space. And y is somehow related to x. So by observing y, we want to further go back and estimate the x. The way we estimate this is to, first of all, we build a estimator on the random variable y. Now this estimator, you can view it as in general, a function of random variable y. So this is another random variable. And we want to find a principled way so that such a random variable is close to the underlying random variable x. Therefore, the way we formulate this problem is to minimize the error between these two random variables, the square error, square distance. This is the truth, this is the estimation. And the square the square distance of a random variable. So we introduced this definition last time. Such a Euclidean distance in the probability space is denoted as the second moment. So this equals to the second moment of this. The entire random variable. Now we want to minimize over all the possible choices of the estimators x hat. Right? And in different cases, we may consider different classes of estimators. And to solve this minimization problem, we introduce this orthogonality principle. So basically, the minimizer, we can use this principle to obtain the minimizer. So the minimizer estimator x hat should satisfy this principle, which says that the difference x minus x hat, this difference, this random variable should be orthogonal to any other random variable z from this class. So this is kind of projecting the random variable x onto this set x, sy, right? So that the projection point is perpendicular to all the other points. And based on this principle, we derived these three MMSE estimators for three different classes of estimators. The first one is called constant MMSE estimator, while the corresponding estimation class is a constant estimation. So if we want to perform constant estimation, then the best choice turns out to be by leveraging this orthogonality principle, we can derive that the best estimator is the expectation of your underlying random variable x. And the second one is linear MMSE estimator, where the class is a class of all linear functions of the random variable y. And we have derived that the corresponding, the best estimator from this linear class takes this form, right? So it's a linear function of y. And this function also depends on the mean value of x and y, as well as their covariance and variance. So all these first order and second order statistics of these two random variables. And in the most general case, we look at the MMSE estimator. Well, there's no constraint on the estimator class. And in this case, the best estimator turns out to be the conditional expectation of x given y. Right? So this we have, when we introduce the conditional expectation, we know that this is another random variable that can be viewed as a function of the random variable y. So these are the three estimators that we introduced last time. And in particular, these estimators have some connections in some special cases. For example, if x and y are independent, meaning that observing y does not tell anything about x. In that case, we can see that the MMSE estimator, this one, the most general one, becomes the constant MMSE estimator because x and y are now independent. So this conditional expectation equals to the expectation. Right. And this makes sense because in this case, your observation does not tell anything about the underlying random variables. So the best you can do is to propose to estimate the underlying random variable as a constant. And in the second case, if this x and y are joint Gaussian random variables, then the MMSE estimate, this conditional mean estimate, is equal to the linear MMSE estimate. So basically, if x and y are joint Gaussian, then this conditional mean takes such a form, such a linear form. Well, we can see this from a very special case. For example, if we consider now they are jointly Gaussian. Now, if we further assume that they have zero mean and have correlation coefficient rho, so that their joint PDF is given in the previous lectures, right, when we introduced joint Gaussian random variables. Now, in that case, we have shown in the previous lecture that this conditional mean is equals to the correlation coefficient times the random variable y. Okay, you can go back and check lecture 19. So given these conditions, joint Gaussian zero mean correlation coefficient rho, we can calculate this conditional mean. Right. So this, in this case, this MMSE estimator is actually rho times y. So it's a linear estimator. Now, also in this case, if you look at the linear MMSE estimator, now the mean are zero. So these two are zero. And this one, covariance divided by sigma y squared. This is exactly the correlation coefficient rho. So in this sense, these two estimators, they are the same. Right. So basically for joint Gaussian random variables, it suffices to use linear estimators. And here's an example on application of this MMSE framework. So we are given such a joint distribution over X and Y. And this joint density is supported within this rectangle. And the density value is depending on X plus Y. So it is not a uniform distribution, right? Okay. Now, given this density function, given this joint distribution, find and compare the LMMSE and MMSE estimates for X and Y with the following joint PDF. Well, to calculate these estimates, basically, now here I list all the estimates. Basically, you just need to follow the formulas and calculate the statistics. For the constant MMSE, it is given as the expectation of X. So given this joint PDF, you can do marginalization and calculate the mean of X, right? So for the linear MMSE, you need to calculate all these different statistics: mean of X, mean of Y, covariance, variance of Y, right? Once you have those, you can just plug them in and get the estimator. For the MMSE, you just need to calculate this conditional expectation. So here we are given this joint PDF, so you can calculate the conditional PDF. Once you have the conditional PDF, you can do the conditional mean, right? So everything reduces to calculating the statistics of these random variables, and also doing some marginalizations of the joint PDF. So here, in order to calculate everything, we first derive the marginalized PDFs, FY, FX, as well as the conditional PDFs. But we need these PDFs in order to calculate the statistics later. So the marginalization part, I will skip it. We have done this in the previous lectures. And here is a rectangle shape, which is very easy to do marginalization. And turns out that the marginalized PDF takes these forms. And then based on that, the constant MMSE is basically the mean of X. So you basically leverage the marginalized PDF of X to calculate the mean of X. And now let's look at the linear estimator. The linear MMSE estimator takes this form. So we need to calculate the mean of X, which has already done in this part. So for the mean of Y, we have the marginalized PDF here. So we can calculate that following the same approach. So we can get this number. And then the variance of Y, right? The variance of Y is on the denominator. So to calculate that, we can leverage this formula for the variance. It's the second moment of Y, subtracting the mean of Y to the power of 2. The mean of Y has been calculated, so we just need to calculate the second moment of Y. Now the second moment of Y is given by this integration. Right? So it's Y integrating over Y squared times the PDF of Y. Now, in the end, you can get this variance of Y. Now, the numerator term is the covariance between X and Y, which is given by the correlation minus the product of the mean. These two mean values has been calculated, so we just need to calculate correlation. But the correlation is the expectation of the product, so we can just take a double integration of this product times the joint PDF. So it's a double integration. And in the end, you get a negative result. So the covariance between X and Y, they are negative. Now, once you have everything, you just plug them into this estimator. So you get such a estimator. So the estimated x is given as such a linear function of y. Okay. So this is the linear MMSE. For the general MMSE, which is given as the conditional mean, okay, we just calculate this conditional mean by leveraging the conditional PDF. Right? Now, so this becomes an integrating over x times this conditional PDF dx. And in the end, it should be something depending on y. So apparently this conditional PDF depends on y. So once we integrate over x, we can view y as a constant. So it turns out that this is the conditional mean. So in general, this conditional, this MMSE estimator is given as this fraction form. Right. Well, here we can replace the realization of y by the random variable y. So this is the general MMSE estimator. We can see that this is a nonlinear form, right? And while the linear MMSE estimator takes a linear form. This is because for this estimator, we do not have any constraint on the estimator class. So it's the minimization is done over a bigger class. So we should be able to get a better estimator, which can be nonlinear in general. So this shows that how to calculate these estimators. Basically, it reduces to computing all these statistics. Okay. Now, once we have these many different MMSE estimators, we want to know some of their fundamental properties. For example, when we do binary hypothesis testing, right? Once after we introduce the MAP rule or the maximum likelihood detection rule, we want to know about the error of probability or the probability of error. We want to know how well this these estimators performs. So here we want to look at the similar properties of these estimators. Now, given these different types of estimators, we want to know their, for example, their error probabilities or some bias. And so these are the fundamental properties that we care about. So we first look at the MMSE estimator, which means that the estimator class is unconstrained. Right? And we care about the estimation error, which is the difference between the underlying random variable and your estimated random variable. So this epsilon is again a random variable. Right? So it's a random variable that corresponds to a difference of these two. And the mean square error is denoted as the expectation of the epsilon square. So it's the error square taking expectation. This is the MMSE framework. So we are trying to minimize this mean square error. So let's compute some basic properties of this estimator. The first thing is that the bias. And in this case, the general MMSE estimator is an unbiased estimator in the sense that the mean value of this estimator is the same as the mean value of X. So how to prove that? Well, we just we can consider the mean value of this difference. Yeah. So the expectation of this epsilon, now the epsilon is defined as the difference of these two. Epsilon is defined as x minus your estimator. Now we take expectation. We know that the MMSE estimator, this estimator is given by this conditional expectation, right? So this x hat MMSE is given by this expectation of x given y, this conditional expectation. Right? So this is our estimator. So we get this nested expectation, right? Inside is x minus our estimator. This is the MMSE estimator. And then we take expectation outside. And because the expectation is a linear operator, right? So we can separate these two terms. So we take the expectation of the first term, and apparently the first term is only involves the random variable x. So we take expectation over x. But the second term is a iterated expectation. Right, so inside is this conditional expectation. So inside is something depending on the random variable y. Right. And outside we are taking expectation over y, the iterated expectation. Now the first term is the mean of x, while the second term by the iterated expectation is simply ex. Right, because we can, the expectation of x equals to, now first we can condition on another random variable y, take this conditional expectation, and then further take expectation over y. In the end, we get the mean of x. So this shows that this is 0. Okay. 0. So this means that, okay, the mean of x equals to the mean of your estimator, right? Inside, here's your estimator. This one is your MMSE estimator. Right. So this shows that expectation of your estimator your MMSE estimator is actually equal to the expectation of x. And we call this property unbiased, meaning that there's no bias in terms of the mean value. Okay, their mean value, your estimator's mean value matches the mean value of your underlying random variable. So at least they coincide with each other on this fundamental statistics, the mean value. Right, so at least the mean is accurately given by this estimator. So this is one of the key messages. And the second property, we can further look at the other properties. So it turns out that the error, this error random variable is uncorrelated with this with your estimator x hat, with your MMSE estimator. Well, uncorrelated meaning that if you recall the definition, uncorrelated meaning that the correlation between two random variables equals to the product of the mean, right? So this is called uncorrelated. Or it is equivalent to say that the covariance is equal to 0. Right? The covariance is basically the left-hand side minus the right-hand side. So to show that, to prove that, we just need to prove that these two, their covariance equals to 0. Okay, this is the error random variable x minus x hat, and this is your x hat, the estimator. And this is how we calculate the covariance, right? So by the definition of covariance is the expectation of the product. Now the product is between the error random variable and your estimated x hat. So here I ignore the superscript MMSE. As this correlation minus the product of their individual mean. And we have shown in the previous part that this error, the expectation of this epsilon error is 0, right? It is unbiased. So this one is actually 0. So the entire term, the second term is 0. So we just need to look at the first term. The first term is the epsilon times x hat taking expectation. So it's expectation of epsilon times x hat. But epsilon is defined as the error signal, right? So x minus x hat is this random variable. Now x hat is your estimator. And by the orthogonality principle, this has to be 0, right? The orthogonality principle says that this one should be perpendicular to n in z from your estimation class, right? And apparently x hat is one of the must belongs to the estimator class. So by the orthogonality, so this expectation, this term, if we write it in using the vector space notation that we introduced last time, is the dot product between this one and x hat. So by the orthogonality principle, these two must be orthogonal. So their dot product must be 0. So now in the probability space, dot product between two random variables is defined as the correlation between these two. Right. So because x hat is calculated following the MMSE framework, the minimum mean square error framework, so it must satisfy the orthogonality principle, right? And the orthogonality principle says that this x hat must be perpendicular to the error, right, this random variable. So the first term is also 0. So 0 minus 0, we get 0. So this shows that the error, this epsilon error, is uncorrelated with this estimator, which is basically to say that the error is perpendicular. This is x minus x hat. This error is perpendicular to your estimate to all the other points on from your estimator class. So this is not that surprising given this orthogonality principle. Okay, so we have this. So for this MMSE estimator, we know this is unbiased. We know that it is uncorrelated with this error. Now, the last question that we want to ask is, what is the mean square error achieved by this MMSE estimator? because this estimator is derived by minimizing the mean square error, right? By minimizing x minus x hat y. Okay. This MMSE estimator is computed by solving this problem. And the question is, okay, now once we have this estimator, if we plug it in, I plug this estimator into this mean square error. What is the actual mean square error that this estimator achieves? Right. So we can plug it in and compute this expectation term. So let's compute the mean squared error achieved by the MMSE estimator. Right? So it's basically the epsilon MMSE, which is defined by this, the difference between these two. The epsilon to the power of 2 taking expectation. This is exactly the mean square error. Okay, so let's look at that. So this mean square error is basically epsilon MMSE square taking expectation. Right? Well, this epsilon MMSE is x minus x hat. So it's a difference between x and this MMSE estimator. Now the first thing we claim is that the first thing we can observe is that because this epsilon MMSE is unbiased, this guy is it's not unbiased. It has zero mean. This error has zero mean, so that from here we derive that the estimator is unbiased. Now, because it has zero mean, so this second moment equals to the variance. Right? Because the variance equals to second moment minus the mean to the power of 2. But now the mean is 0. So this guy is actually equals to the variance. So this is how we calculate this term. Okay, and in the end, we can show the result equals to the variance of x minus the variance of your estimator. But let's see how this result is derived. Basically, we start over again. We want to look at this mean square error achieved by MMSE. Now, writing it out, it is basically this mean square error. Again, so this is definition, x minus x hat. And here I ignore the superscript MMSE. And this is a quadratic term, so we can expand it right into 3 terms. One is x squared, x hat squared, minus 2 times x hat. And then for these 3 terms, I apply the linearity of expectation. So the expectation can be applied to each term separately. Now let's look at each term one by one. These two are second moments of x and x hat, so I keep them here. Okay. I did not change anything. For this cross term, this cross term can be simplified as follows. So x, maybe I can write it here. So x equals to epsilon plus x hat. Right? Because epsilon the error is defined as x minus x hat. Right? X minus x hat is epsilon. So epsilon plus x hat is x. Right? This is definition of epsilon. Now why do we want to replace x by epsilon? Because we know the epsilon satisfies many properties. Now, by doing so, we can decompose this term into two terms. Into these two terms. And the first term, right, by the orthogonality principle, right here, by the orthogonality principle, epsilon and x hat, they are uncorrelated. So this is 0. Okay? So this can help me simplify and remove this error term implicitly from this product. So what is left is only the second moment of x hat, right? It has nothing to do with x now. So this correlation term, right, turns out to equals to the second moment of x hat. Right. So this one becomes -2 second moment of x hat. And we get rid of x in this cross term. And this is the tricky part. And once we do that, these two terms can be combined. So we get minus the second moment of x hat squared. Okay. Now, from here to here, let's see, these two terms are exactly from the previous line. Okay. And we introduce these additional terms, x and x hat. Well, we subtract the mean of x to the power of 2, and plus, you see there are two negative signs here, and plus the mean of x hat to the power of 2. Right? These two are equal because we have shown that they are unbiased. Right? Ex, mean of x equals to mean of x hat. So by introducing these two, they can cancel with each other. Right? So this is equality. We did not introduce anything here. And these two. And you see, this is very different because this is the mean to the power of 2, right? This is very different from the second moment. Okay, by introducing that, we can, now the first two terms can be combined by definition as the variance of x. Now the second two terms can be combined as the variance of x hat, right? So in the end, we can conclude that, okay, the mean square error achieved by the MMSE estimators given by the variance of x minus the variance of your estimator. Right, so this is the formula that we can leverage to calculate to evaluate the performance of this estimate. And of course, an alternative form is to ignore these mean terms because these two terms get canceled out. So if we stop here, then we can conclude that the mean square error of MMSE is basically the second moment of x minus the second moment of x hat. Right? And because x hat is defined as the conditional mean, right? This MMSE estimator is defined as the conditional mean. So we can plug it in. So it is conditional mean to the power of 2, and then further take expectation. Right, so this is the analytical formula for computing the mean square error for the MMSE estimator. Right. And to do that, we need to compute the second moment of x. If we know the PDF of x, we can do that. And we also need to compute the conditional mean and then the second moment of this conditional mean random variable. Okay, if we know the joint distribution between x and y, I think these terms, all these terms can be computed one by one. Right. So this is the MMSE estimator, which is derived by the framework with an unconstrained estimation class. And we can also look at the linear MMSE estimator, which is not very different from the MMSE estimator. So the linear MMSE estimator is given by this form, right, from the previous slides. This is the linear MMSE estimator. Now let's look at all these statistics. The first one is the bias. Right? The bias is defined as the expectation of this error. Right? Well, this error is basically the difference between your underlying random variable minus your estimation. So this is the error, and you take expected value of this error. Now you can see that it is equal to 0. Why? Because by linearity of expectation, right, I can evaluate the expected value of all these terms one by one. Now this is a universal constant, EX, the mean value of x. The constant, though, so this expectation applied on this constant is still this constant. But the first term, x, random variable x, after applying the expectation, this one becomes expectation of x, and it will cancel with this mean value, right? So in expectation, these two gets canceled. And similarly for this term, for the second term, right? These coefficients, they are constants, covariance, variance. This is the mean of y. These are all constants. By linearity of expectation, this outer expectation will go into this random variable y. So this, after applying the expectation, becomes expectation of y, gets canceled with this term. So all the terms gets canceled out. You get 0, right? Which means linear MMSE estimator is also unbiased. This is a very nice property. At least the mean value is accurate. And then we can calculate the mean square error achieved by the linear estimator. Okay? And because it is unbiased, so I think all this derivation from the previous case holds, right? We just do a quadratic expansion, and here we utilize the orthogonality principle to simplify that, right? The expanding the quadratic expression is always is universally holds everywhere, right? And this orthogonality principle also applies to all these cases. So this result also applies to the linear MMSE case, right? So in the end, the mean square error is basically the variance of x minus the variance of x hat, your estimator. But the only difference is that now we are looking at the variance of the linear estimator, whereas in the previous case, we are looking at the variance of this MMSE estimator. So the estimator are different. Okay, so now let's look at the variance of this mean square of this linear estimator. This is variance of x minus the variance of this linear estimator, right? This is the linear estimator. Okay, now look at this. Inside is a linear function of y, right? So it is something like ay plus b, right? Well, the no, the A equals to this coefficient, right? This is A times Y, right? And all the other terms, the expectation of X and the expectation of Y times this coefficient, they can be combined and viewed as this constant term B. And we know that the variance, by the variance formula, this is equal to A squared variance of Y. So we just apply that. It's basically equals to this coefficient square times the variance of Y. Right. And you simplify that, these two can be canceled. You get this mean square error. Right? So the mean square error of the linear estimator, linear MMSE estimator, is given by the variance of X minus, right? This term is the covariance to the power of 2 divided by the variance of Y. Right. So in the homework problems, you don't have to go over this proof again, right? So you just need to leverage these formulas to calculate the mean square error achieved by different estimators. And in the end, you see from these formulas, in the end, it reduces to computing these fundamental statistics of these random variables. Okay, so this finishes the MMSE estimation. We introduced different types of MMSE estimators. Right. Linear. I think the most frequently used one is this linear one and this MMSE one. These two. The constant one is trivial, so we will not pay attention to that. And then we know how to compute. We know that for both MMSE and the linear MMSE, these two estimators, they are unbiased. Both of them are unbiased. And their mean square error is given by these formulas. Okay. So this is everything about the minimum mean square estimation. Okay. And from now on, next we are going to step into the higher dimensional space. We're going to talk about n-dimensional random vectors. So previously we have discussed everything about a pair of random variables, right? The joint distribution between two random variables and the functions of two random variables. Right. Functions of two random variables. We know how to compute this PDF, CDF. So everything is about up to a pair of random variables, basically two. Now we are going to generalize, extend everything to arbitrary number of random variables. So basically, from 2-dimension to high dimension space. But I would say, except for well, of course, when we go to higher dimensions, we will involve more and more random variables at the same time, which inevitably makes everything more complicated. But although the notation looks a bit complex, but I think all these concepts, they follow exactly the same idea, except for that we are dealing with more random variables at the same time. So let's try to develop this the concept of n-dimensional random vectors. Now, in the previous case, when we say two random variables, for example, we say x1, x2, right? These are two, each of them is a single random variable. It's a mapping from omega to a real number, right? So basically, when you observe the realization of each random variable, it is a single number. For each random variable, is a single number. But now we can generalize this idea by stacking a bunch of random variables into a column. And we call this a vector of random variables. Right? It's a very natural idea. If you imagine each random variable as a coordinate, because its realization is a number, right? You can stack them into a vector. Right. So all these x1 to xn inside, each of them is a random variable. So you can say this is a mapping from omega to the Rn space, right? Because for each omega, for each outcome, each random variable will give us a response, will give us a real number, a realization. Right? Each realization of the random variable will give us a number. So all these numbers get together, becomes a vector. So this is how we write these random vectors, right? So we will use these notations throughout. So this x is a random vector, and this y, again, is another random vector. And the joint PDF, right? Well, basically, if this n and m equals to 1, then this random vectors reduces to a single random variable. Right? So this is a natural extension to the n-dimensional, so-called n-dimensional space. And for these two random vectors, we can define their joint PDF. Right. So basically, put all the vectors, replace the order vectors by the. I think here should be capital ones. So this should be a typo. So what does this precisely mean? Well, it basically means the joint PDF among all the random variables involved in x and y. Because x1, x2, xn, y1, y2, ym. Right? Because these are the random variables involved in these random vectors. And the inside is the realizations of these random variables. So it's small x1, small x2, small xn. Right. So everything is a straightforward extension of the two random variable case. Right? Before we have x1, y1, the two random variable, but now everything can be extended. Now for notation simplicity, right, we write this in terms of this vector form, x and y, random vectors. And we can now we define this basic random vector, right? You can view each random vector as a big random variable in a higher dimensional space. And we can define its mean value. The mean value of a random vector is defined as the vector of these mean values coordinate wisely. So basically compute the mean of each random variable in every coordinate and stack all the mean values into a vector. We call this the mean value of this random vector, which is again a vector. Right. So you see, this is kind of the only natural way to define, to extend these definitions to vectors. You have to do them one by one, coordinate wisely. But in the end, it reduces to calculating the mean of a single random variable, right? So we can handle this. And also we have this, we call it correlation matrix, or sometimes we call it autocorrelation matrix. But it basically mimics the definition of correlation of two random variables. Okay. For two random variables, the correlation is defined as Ex and Y, right? Correlation. But now for two random vectors, it's defined as X, Y transpose, right? Which means now X is a column vector, so X1, X2, Xn. Now Y is also a column vector, but after applying transpose, it becomes a row vector. Now this is a column times a row, it becomes a matrix, right, by the matrix multiplication. So this matrix is X1, Y1, X1, Y2, up to X1, Ym. Okay. Just see it's a pointwise product for all the pairs of these different X and Ys. And X2, Y1, I will not go over everything, so it's, in the end, it's Xn, Y1. The last one is Xn, Ym. Right. You have this matrix of product of random variables. In this matrix, every entry is a product of two random variables. Now you take the expectation. Now, apparently, this definition is defined precisely this. The expectation of this matrix is simply defined as the matrix of these entry-wise expectations. This is the only way that we can define this expectation in a meaningful way. Right. So essentially, it is reduces to computing this, evaluating these correlations between these random pairwise random variables from these two random vectors, right, pairwisely, and collecting all these correlations into such a matrix. Right. So we call this the correlation matrix. Correlation matrix. This is basically a correlation matrix between two random vectors. If each random vector only involve a single random variable, x1, y1, then this matrix will only involve the first term, right, which reduces to the correlation definition of a pair of random variables. Okay. And here we call this, okay, this correlation matrix is defined for any arbitrary two random vectors, x and y, right? Correlation matrix. Here we call this one, we add an auto in front of this. We call this auto correlation matrix. When y equals to x, when we are looking at x transpose. So it's like the correlation matrix between x, the random vector x, and itself. So we add an auto in front of that in this case. Yeah, and we give it a special notation, Rx correlation. Okay. So according to this definition, this autocorrelation matrix is, again, basically you list out all the, this is a column vector, and X transpose is a row vector. You multiply these two, get this matrix, all the Y's becomes X. And you get, in the end, you get this entry-wise expectations. And because it is autocorrelation between X and itself, we can see that on the diagonal entries, these diagonal entries, they actually correspond to the second moment of each random variables. Right. And all the off-diagonal entries, they are the correlations between different pairs of random variables involved in X. Right. You can, in fact, this is actually very simple to understand. This correlation matrix is basically a collection of the pairwise correlations among all the random variables involved in these random vectors. These are different pairwise correlations. And we can also define this auto covariance matrix. It's basically defined as, you can write this one, CX. This one looks very similar to the covariance definition of a single random variable, right? Except that we replace X by the vector, a random vector. So it's the random vector subtracting its mean multiplied by the transpose. You see, this random vector is x1, x2, xn, right? By definition, the mean, you go back to the mean is defined as this mean vector. But it's well defined. So this is the first term. The second term is the transpose of these two. Right? See, it's a column vector minus column vector. In the end, it is a column vector. Right? So this is the first term. Now the second term is the transpose of this column vector. So it is a row vector. It's a row vector. This is a column vector. So again, column vector times a row vector, you get a matrix. Right? Column vector times a row vector, get a matrix. But you don't have to expand it entry-wise. You can just follow all the matrix matrix multiplication rules. For example, you can just expand it. This is x minus. You just need to remember this is a column vector and that is a row vector. So you can know the vector to the transpose. We can put the transpose inside. This is our own linear algebra. And you just multiply this. one by one. You have X transpose. This is a column vector. This is a column vector transpose. It's a row vector, but we can write it in this way: column times a row. It is matrix multiplication compatible, and you have X times EX transpose. You have here you have EX times X transpose, and you have EX transpose. Right. And these two, these two, they are not equal to each other, right? They're not equal to each other, because for matrix multiplication, right, A, B transpose, I think in this case, they might be equal to each other. AB transpose and BA transpose. They are not equal to each other, because this one is A1, A2, AN times B1 to BM. But this one is B1, BM times A1, AN. Comparing their first row, the first row here is A1 times B1, A1 times up to BM. So everything has A1. But here is B1 times A1, B1 times up to AN. Everything has B1, right? So they are different. So you have to be careful when you do linear algebra. These two, although they look very similar, but they are different. They are equal only when they only have dimension 1. So both of them is A1, B1, B1, A1. This is the only case when they are equal. But in the high dimensional case, these two are not, they're not equal. But in the end, there's still another expectation outside. So you can, by the linearity of expectation, you can just apply them to. So sometimes I will ignore this arrow for simplicity by assuming that everything here is now a vector, okay? X transpose. And also by default, all the vectors is in a column by default, just as we, this is a convention adopted by MATLAB. And when you define a vector, it's always a column vector. Will only apply to this one. EX transpose. And this one, the expectation applies to the second one, minus EX transpose. So this should be plus. And plus EX transpose. Right. And now, so after applying this expectation, these two becomes equal. But here, before applying that, they are different. So, but now after applying the outer expectation, these two get cancelled. So you get a formula very similar to the single random variable case. You get this formula. The covariance. This is actually the auto covariance matrix. It's basically the variance of the random vector X. Right? but we call it autocovariance matrix. Covariance means is that is a covariance between two random vectors, and auto means that it is the covariance of itself. Okay. But this is very similar to the variance formula for a single random variable, right? Except that we are now looking at the vectors. So inside you see this is not the second moment of something. It is similar to a second moment of the random variables of a single random variable. But now because it is a vector, so we instead of having x to the power of 2, we have x times x transpose, take expectation. Right. Well, x times transpose is defined as such a matrix. This is the first term. And the second term is the product of these two mean value vectors. Right. So to be more explicit, for the second term, we have EX times EX transpose, which EX is the mean value of all these random vectors, and then EX transpose is the row vector. Now, once you multiply these two, you get EX1 square. So you basically get EXI times EXJ, right, for all the IJ pairs. And this is different from the first matrix. In the first matrix, it's the matrix of correlation, right? It's the expectation of the pairwise product. And this matrix is the pairwise product of the expectations. But if we write it into the matrix or vector form, you can see the similarity, right? So this is very similar to the one-dimensional case. Of course, in the more general case, if we want to look at the covariance between two random vectors, x and y, we call this the cross covariance matrix. That's following the same definition, but now we are looking at the covariance between x and y. So here's y instead of x. And this formula will become this one, okay? The x transpose part becomes y transpose. Right. So the only difference is that we are now involving more and more entries, more and more terms. But if you write them into a vector form, the formula stays the same. Right? You just need to pay attention to this transpose. Okay? Because now we are doing linear algebra, matrix multiplication, instead of multiplication of numbers. So this matrix, this cross covariance matrix, is not necessarily square, because X may have, this may be a n-dimensional column vector. This could be a m-dimensional row vector. So the size could be a rectangle. Right? But the autocovariance matrix is a square because it is X correlated with itself. So the dimension is n by n. Right? So these matrices, correlation, covariance, these matrices is a collection of these fundamental statistics among all the pairs of random variables involved in these random vectors. So there's nothing, except for this notation, the complex notations, there's nothing else that is surprising here. in the end, everything reduces to the expectation, to the statistics of a single random variable. Okay. And these matrices has some very simple intuitive properties. If all these random variables are pairwise uncorrelated, then the autocovariance matrix is orthogonal. Well, you look at this autocovariance matrix, this one, right? This CX matrix, the ij's entry is given by, right? The ij's entry is picking up the ith row j's column, so it is indexed by so the ij's entry of this matrix, right, is the ith entry is the ith row of this column vector times the j's column of this row vector. The ith row of this column vector is just xi, and j's column of this column vector is j's column of this row vector is xj. Now they are pairwise uncorrelated. Right. Pairwise uncorrelated means that this is basically CXI XJ, right? The covariance between XI and XJ. Now, pairwise uncorrelated means that XI XJ is 0 for any I not equal to J. Pick any two random variables, they are uncorrelated, right? Any two different random variables, which means that most of the entries of this matrix is 0, except for the diagonal elements. The diagonal elements is expectation of xi squared minus this square. Right. All the other terms are 0. And this is basically the definition of the variance. Of the variance, sigma 1 squared, sigma 2 squared, up to sigma n squared. Right. So basically, if these random variables in the random vector x, they are pairwise uncorrelated, then naturally this autocovariance matrix can be much simplified. So most of the covariances are 0, so they are uncorrelated. The only correlated ones are the diagonal elements, which these diagonal elements corresponds to the correlation of each random variable with itself. And of course, in that case, it becomes the variance of this random variable, the covariance between these random variables and itself. Right? So it becomes the variance. This is a very special case. We will see it many times. Yeah, so I think we can leave it. This one is to say that if we are talking about more general cross covariance, I think the idea is the same. Right? Everything is 0. If x and y are pairwise uncorrelated, these off-diagonal entries will be 0, and diagonal ones will become the covariance between x and y. Yeah, between the pairwise x1 and y1, x2 and y2. we can go over that in the next time. Yeah, okay, I can stop here. So you can see that once we go to this n-dimensional random vectors, I think the basic idea is exactly the same, but we just need to be careful about the matrix vector notations and be careful about the matrix multiplication, linear algebra, all those kind of stuff. Okay, so I will see you in the office hours this afternoon.